Hello, my name is Oshi, and in this short video, I'm going to explain how you can construct a calibration curve. Okay, now calibration curves are used to relate an experimental unknown to a known quantity or value. Okay, so what does that mean? All right, well, let's say we had some aspirin tablets. Okay, some aspirin tablets, and we put them into a beaker of water, and we want to determine how quickly and how much aspirin gets released over a period of time. Well, of course, we can put the aspirin tablet into the water, and then we can withdraw some samples of the solution, right, at different time points, 5 minutes, 10 minutes, 15 minutes. And then we can place that solution into our UV spectrometer, okay? The UV spectrometer doesn't tell us the concentration of aspirin in solution. It tells us the absorbance of that solution, okay? And what we can do is relate that absorbance value back to a known quantity of aspirin using a calibration curve. Now, calibration curves are used all the time in pharmacy, and they don't necessarily need to be used to calibrate drugs. You'll see in the video that I'll upload, or the second part of this video, that a calibration curve could be used, for example, in FTIR to maybe measure the concentration of something like ethanol in a hand sanitizer gel. It can be used, as I say, in aspirin release studies, or it could be used to monitor the degradation or the stability of a certain compound, or something that maybe bacteria produce or metabolize. So really, really useful, and used in many places, in many contexts, in pharmacy and in pharmaceutical sciences. So what do we do? What do we mean by relating absorbance back to a known value? Well, if we have a concentrated stock, and I have an example here of concentrated stock, let's say it's 1 gram per liter in concentration. Well, if I dilute that solution by half, right? So I perform a 1-in-1 dilution. 1 gram then goes to 0.5 grams per liter. Then diluting that by half, 0.25 grams per liter, and so on. And these solutions of known quantity will have their own absorbance reading, okay? And we record the known quantity in terms of concentration versus the absorbance value that we read on an Excel spreadsheet, and then we can create our calibration curve, hopefully, in a linear plot. So let's kick off. Let's get down to the experiment. Let's see what we need. Let's see how we actually conduct this and create or construct our calibration curve for this sample of food dye that we're going to dilute down, okay? All right, using our equipment. So what we need, all right, we need a pipette. Of course, we need a UV spectrometer. We need some diluting agent. In this case, I just use water, all right? You want your diluting agent to be something that your drug or compound is going to be soluble in. And in this case, our solution is, our food dye is made up in water. We know it dissolves in water, so water will work just fine. And we need some vessels as well to dilute up our substance, okay? For those of you that perhaps haven't seen an apparatus like this is called a pipette, all right? And the pipette is calibrated, and it allows us to deliver a precise volume of solution, okay? And this pipette, you can see, is calibrated between 0.1 mil, or 100 microliters, and 1 mil, okay, or 1,000 microliters. And we can see that I've set this pipette to 1,000. Some other pipettes, like this Gilson pipette, also, you hopefully can see, deliver a volume between 100 microliters and 1,000 microliters, or 1 mil and 0.1 mil. Instead, their number system only has 3 numbers, okay? All right, sometimes a little bit confusing for those that haven't seen it for the first time, but for these types of pipettes, this is set. The 1 is the maximum value, okay, and it's set at 1,000. Of course, if I just tune this down, let's say we put it at 900 microliters, you can see that now it says 0 at the top, and so that's what we're using, okay, to guide ourselves, all right, in terms of the volume that this pipette is set to. Some other final tip is that when you use a calibrated pipette, you must never exceed the maximum, in this case it's 1,000, or go below the minimum. Again, as we say, 100 is that minimum, okay? And we have these blue pipette tips, which are used, you don't directly drop the solution into the pipette, you must always use a pipette tip, all right? And the easy way to load a pipette tip onto your pipette is you just take a blue tip box, push the pipette into the tip box and remove it, and you've got your nice pipette tip on top. To eject the pipette tip, there's a second button here on the side, this lever, and you just press it, and the pipette tip will go directly into our bin, like this yellow bin I have here beside me. Okay, so we understand how to use a pipette, we understand what we have and what we need. Let's get cracking, okay? All right, so I'm just going to place a pipette tip on, and I'm going to get started, all right? Now, the most important thing that we need to know before we construct our calibration curve is what is the volume that we need, okay? Now, what do I mean by that? Well, for example, our UV spectrometer needs 4 mils, right? We need 4 mils to measure a volume in our measure absorbance in our UV spectrometer because of our large cuvettes, okay? So 4 mils. 4 mils basically allows you to fill the cuvette and have a wee bit left over, just in case you make any mistakes, all right? So, sounds sensible. How do I perform a 1-in-1 or half dilutions in each of these volumes and make sure that I end up with 4 mils in each of these vessels at the end, okay? My tip is, if you know what your end volume is or is going to be, to put the volume into each of these vessels first, okay? And this will make sense in a few moments, okay? So I know that I'm going to end up with 4 mils at the end, so I'm going to take my diluting agent and I'm going to put 4 mils of diluting agent in each of these vessels, okay? Placing it into the solution. 1, 2, 3, and 4. And you'll notice that I count them out aloud because sometimes you forget, okay? Humans make mistakes. It's good to count things aloud. It'll keep you on track. And, if you're thinking about the Newcastle match, or you're thinking about, the latest, things you've seen on TV or TikTok, your mind doesn't get distracted, okay? And you can keep count, and, you're not going to make a mistake, all right? So I like to keep count, all right? One other tip. When you're using your pipette, you'll feel that there's 2 stops, okay? To withdraw volume, okay, you push the plunger down to the first stop, place the pipette tip into the solution, and withdraw slowly, okay? And then to eject that volume, you go through the first stop and into the second, okay? So that's 1, 2, so pushing the plunger down, then into the solution, withdrawing, and ejecting. 3 and 4. Great. And I'm just going to speed up through this video. And 4. Okay, so we're back on track again. I'm just going to dispose of my pipette tip. All right, I'm going to get a fresh pipette tip. And now I've decanted some of my concentrated stock into this vessel. And as I said, I'm going to do a series of 1-in-1 dilutions. So let's see how that looks like. So if I've put 4 mils of blank or diluting agent into this, of course, to do a 1-in-1, I'm going to need 4 mils of concentrated stock. 1, 2, 3, 4. Okay, and I'm going to just dispose of my pipette tip, put the lid on, and just give it a little bit of a mix. All right, so nice. We've got 4 mils now. 8 mils of concentrated stock. Now, what I would do is, this is the concentrate. I would put it aside, okay, and now I'm working with this new volume, all right. I get a fresh pipette tip, right? Remember, fresh pipette tip. Every time we've obviously just contaminated our pipette tip with really concentrated stock. So, fresh pipette tip, and again, from this new vessel, 4 mils. Okay, so we're now finished our series of dilutions, okay? I'm just going to put them on the bench, and hopefully you can see that as we have diluted our concentrated stock down in a series of 1-in-1 dilutions, the color gets lighter, okay? And that's expected as we've diluted up the substance that's going to be placed into the spectrometer for our calibration curve, okay? On to the next part of the video then. I'm going to place these into the spectrometer, record the results, and then we're going to see how we approach analysis.
And so in this example, I'm using a HPLC system, and the HPLC system, when I measure the behavior of a drug compound in solution using that HPLC system, it will give me a value of the area under the curve. And of course, that area under the curve is an unknown quantity, right? I don't know what that means, and I want to try to translate that area under the curve value into a known quantity, right? And so I want to transform, in this case, in this example, I'm transforming that experimental value of area under the curve to concentration, right? And so one of the ways I can do that is by preparing a solution of known concentration, right? And so you can see here in this Excel sheet, I've prepared a solution that has 10 milligrams of nitrofurantoin per 100 mil, right? And that will give me an area under the curve of 701.3. I then can prepare another solution of 5 milligrams per 100 mil, and that will give me this corresponding area under the curve, and then so on, okay, until we have a complete a chart, right? We normally want about 5 points, okay, you know, of varying concentrations with the corresponding area under the curve to create a calibration curve, okay? And so then we create our calibration curve, and we have some unknown quantity, right, x, some unknown concentration, and let's say that that experimental value gives me an area under the curve of 500, right? So the system, the machine measures or tries to detect the concentration of drug in solution, but it provides me with an area under the curve value, okay? And that area under the curve value needs to be translated back to concentration, right? And of course, we can spend many, months or years of our time trying to find the exact concentration that's going to provide an area under the curve of 500. Or, as I mentioned, we can create a calibration curve where we take a couple of different known concentrations, find their areas under the curve, and then construct a chart like this, okay? And so what we do, and what I did in this example, was I took all of my data, right? So I'll delete the chart. Once I have my data, I take all of my data, press insert a scatter plot, okay? All right, and I'm going to delete the chart title, and I'm going to increase the size of the text so it's quite clear for me, okay? And then the final thing that I do then is I right click on some of the data points, right? So I'll click off the data points, and I'm going to right click on data points, and I'm going to press add trend line, okay? Add trend line. Then this dialog box will come up, okay? I want to fit a linear model, right? A linear model. I want to display the equation on the chart, okay? And I also want to see the R squared, okay? The equation of the line allows me to translate any of these y values, right, that I'm going to determine experimentally. It allows me to transform any of these y values into an x value, right? And the x is concentration, right? And y is area under the curve. So if I have any y value, then using this equation, I can transform this into an x, okay? And so we see this other value, the r squared, and the r squared, in essence, tells us how well our trend line fits our data, okay? An r squared closer to 1 is really great. It's a really strong correlation, right? And an r squared that's lower than 0.9 or 0.8, we start to lose confidence, okay? And certainly in your experiments, as you move through the pharmacy program, if you find that your r squared value is really lower than 0.9, then I would start to be asking questions, right? Maybe you made an error when you were preparing your solutions of known concentration, or maybe you made an error in the measurement of whatever value it is. And in this case, for my experiment, it was area under the curve, but for yours, it could be absorbance. And so let's then take this equation and translate our y value into an x, right? The unknown concentration, okay? And what we can do then is we rearrange this equation, okay? And so if 500 is our y value, okay, and we want to find an x, we rearrange this equation for x, okay? And the first thing we do then is we look at our equation, 2.7433 from 500, and then of course we need to bring 71 over, and we can divide that on both sides, 71.073, and then we get our value then of 6.99, or roughly 7 milligrams per 100 ml. So that tells us that this experimental value of 500 translates to a concentration of 7 milligrams in 100 mils. Okay, so it's a really useful technique that allows us to, again, with an experimental system like the UV spectrometer or a HPLC, where we're going to get an experimental value of an area under the curve, or we're going to get an experimental value of absorbance, which doesn't really have any meaning to us, well, we can then give that value a meaning by constructing a calibration curve. And again, we construct the calibration curve by simply measuring the experimental value from a series of known concentrations, constructing a plot, inserting a linear trend line, and using our equation then translating any of our experimental values, right? Using that equation into a known concentration. Okay? So I hope that makes sense. A calibration curve allows us to transform experimental values into values that make sense, right?
And so in this example, I'm going to show you another application of the calibration curve and the calibration standards to identify an unknown. What we have in this chart is a series of calibration standards done in FTIR. And on the left, you can see the entire spectrum. And on the right, you can see a zoomed in spectrum in a region of interest, and that's these two peaks, where I created a bunch of calibration standards of ethanol, and you can see that these peaks are sensitive for the concentration of ethanol. So I took the peak maxima, right, as the absorbance, or in this case it was percentage transmission, and the known ethanol concentration that of course was known and was labelled, right, using a known amount of ethanol. Then recording the data. So an ethanol solution of 50% volume gave a transmission of 77%, and so on, okay? And in this context, I was trying to understand the concentration of ethanol in a hand sanitizer, and this was around the pandemic, and I was in the department of chemistry. We had a bunch of hand sanitizers from all different sources, and we wanted to know how much ethanol content was in each hand sanitizer. Of course, we knew then that 70% volume was the ideal for ethanol, and so we were trying to make sure that the products that we had and we were given to our researchers met that standard. And I thought this would be an interesting case study. So you can see in the light grey dots that I have on this chart the calibration standards. Okay, they've been plotted for you, and of course I generated a function and a R-squared value as before, as I've shown you for the HPLC and the UV-Vis examples. And then on top of that, you could use the equation to calculate this analytically, as I've shown you before, but I just wanted to insert those values, right, that I obtained from the different bottles of product X and BHS into this chart, just so you could see where they sit along the calibration curve. And we can see here that BHS 80, there's one product to two bottles. I received a percentage transmission of 66 or 67 thereabouts, and that equates to an ethanol concentration of about 82, right? So really quite high. And product X, the two bottles that I got, one gave a percentage transmission of about 73 or 74, which equates to a low concentration of ethanol of 62%, and then the other really close to ideal with a percentage transmission of about 71.14 and a percentage ethanol concentration then of very close to 70, as I say. So again, just a quick demonstration of, just yet another context where calibration standards can be useful and, help us answer practical problems that we face in the clinic or in pharmacy. Thanks.